Okay, well, good morning, everybody. I hope you had a good day off yesterday, but it's back to work today. Thanks for coming in on this sole day at the end of the week. It's good to see that you're still very excited about joining us, and the practice, of course, are on this afternoon, and I hope that you have another good day. So today is another good day. We've got some really fantastic speakers for you. We are going to feed you well, we promise. Is that right, Belle? Yes. Belle promises we're going to feed you well today, being the last day. You'll also receive your certificate today, and so it should be a good day. Just want to start again by acknowledging the country that we're on. This is the traditional custodians are, of course, the Kaurna people here in Adelaide. We respect their spiritual relationship with the country. Also, just want to acknowledge again our sponsors. I do this many times, but it's because we're very grateful. They're fantastic supports to make this happen, and I think you've enjoyed chatting to them in the breaks. So here they are, and keep talking to them. They love it. I've already talked to them. They've been enjoying the conversations with you. Today we have 5 speakers. So we've got a speaker from all the way from the other side of the world dialing in for us today, Dr. Thorsten Matthias from EVG Group. And then we've got Dr. Barak Kudzinski. That's terrible, isn't it? My pronunciation is awful. You don't even know. Okay, that's a great relief to me. So Barak will teach us how to pronounce that better than I just did, hopefully, at DSD, and Coca Kennedy at DSTG as well. We also have Stephen Blackney from the Medical Device Partnering Program. I mentioned before that this node is across UniSA and Flinders, and we work very closely together, and Stephen spends time actually at both sites, and so really great to have him talking to us today about what's happening at Flinders. And Dr. Leanna Reid, Chair of Carina Biotech and Tech Site, and also a former South Australian Chief Scientist and entrepreneur, and really fantastic leader. So look out for those talks this morning. That should be fantastic. Just to remind you of our little jigsaw here, you will have seen a few talks, and hopefully yesterday you took the time to dial into to watch the recordings that we've got. But Colin has spoken to you about coding. We've had Mariam on photolithography, Dong Hoon on etching, Ben on laser milling. Now, micro milling you would have seen online, hopefully, a recording from Mark. Some really nice work there. Please do check these out. These are fantastic. And Mike on injection moulding and moulding technology. Then today, Coco and Barak. So these are the lectures that you'll see, and of course the insights link all these things together in terms of devices. So by the end of this week you should have a rough idea what steps you could put together to make a small device. These are our volunteers, just thanking them all again, and back to the sponsors. Now just quickly I want to show you again a video. We promised our sponsors we'd do this, so I'm going to do it. Let's see if I get this right. So SciTech is one of our... Let's see. Hopefully this works. I'm going to play you this video from SciTech. I think there's no sound, but we'll just go with it. So ALD is atomic layer deposition. This is a electron beam lithography tool. How's my narration? FIB-SEM, focused ion beam scanning electron microscopy for milling tiny things and looking at their cross-sections. Plasma technologies there. Plasma technologies are fantastic in coating things and etching. I missed that one. And this looks like roll-to-roll processing. Lots of different capabilities that you might use in your fabrication. Spin coating. All of you will see a spin coater in your prac. If you haven't done the clean room prac, you'll be in there today. Baking, of course, is part of the processing that you need to do to cure some polymers often. AFM. Do you know what AFM is? Atomic force microscopy, scanning tiny things to be able to see their structure and the surface topography. There's a family of brands there. Excellent. So thank you to SciTech for their support. And last but not least, oops, oh. Here we go, with sound. So you saw just before there a maskless lithography system. We've purchased one of those for the South Australian node. It will come middle of next year. It takes a while to get these tools in because they're very complex and are made bespoke. Okay, so a little snapshot from two of our sponsors. Now, you can see here there's also EVG as one of our sponsors, and EVG has been an outstanding support of the Winter School for many years and have some pretty amazing equipment. And there's different ways that sponsors support us. In this case, we're especially privileged that Thorsten from EVG has dialed in from the other side of the world. It's the middle of the night, I think, Thorsten, for you, which we're very grateful for you staying up to speak to us. And Thorsten has some EVG has some outstanding, world best capabilities, and Thorsten has some really world best knowledge of those capabilities, and so we've asked him to speak to you today. He's the Regional Sales Director of Asia Pacific EV Group. Prior to his role as Regional Sales Director Asia Pacific, Dr. Matthias was a Director of Business Development specifically focused on 3D integration, MEMS, that's microelectromechanical systems, and LEDs, which I'm sure you all know, and a number of emerging markets. He began his career with EVG in 2002 as the product manager for the SmartView wafer bonding alignment system, and then became Director of Technology of EVG Group North America in Tempe, Arizona. Dr. Matthias received his doctorate degree from Vienna University of Technology with a thesis in solid-state physics in 2002. I'm going to stop sharing so you can see him. And hi, hi Thorsten, how are you?
Hello, everybody.
That's good, we can hear you and you can hear us. We're going to, I think I maximise this screen, is that what you want me to do? Yeah, is that the way to go? I'm maximising the screen so that everybody can see you here in the room. I'm sure they can see you online. I hope that you've had a coffee or something to keep you awake, but we're bright and sparky. It's morning and we're very excited to hear from you today, Thorsten. And so I guess hopefully everyone you can hear us, but I'll get everyone here to give you a big cheer to thank you for staying up late, and we'll hand over to you. You can screen share.
Thank you, Craig. So,
are you able to screen share? Okay, perfect. We've got you. It's all yours.
Is it working?
Yep.
Okay. So, good morning, everybody. So, welcome from my side. So, let's start the day bright and early with some discussions about wafer bonding. So, before we jump right into the technical details, just one word about EVG. We are an equipment manufacturer. We build, for example, mask aligners, brake coaters, spin coaters, and last but not least, wafer bonders. And also one very interesting technology, nano-imprint lithography, which I think you probably have also heard this week already a couple of things about. Okay. So now let's jump into the technology. Let's jump into the details. Let's talk about wafer bonding. So when we talk about or think about a new technology or a technology like wafer bonding, which might not be so familiar to everybody, probably a good starting point is to try to define what we want to achieve with wafer bonding, what is the outcome, what we envision if we apply this technology. And I will address some of these here in the next 30-35 minutes. But just as an outline, wafer bonding is a technology to permanently mechanically connect two wafers to each other. This could be either for the purpose of creating a cavity. So mechanically, I build a cavity in my microsystem where I can either encapsulate vacuum, or I could encapsulate some specific gas or a specific atmosphere pressure. I can use wafer bonding in order to transfer thin layers of one type of semiconductor onto another, basically create a stack of different semiconductors. I can use this to integrate wafers which have been fabricated for example, by different companies or in different fabs around the world. And wafer bonding would be a means to basically create on the micro level, on the chip level, create a system out of various components. I can use it, for example, in order to shrink the form factor. For example, if I have multiple memory wafers and I want to stack them on top of each other, for the purpose of having more memory in my device. And I can actually also use it to create some specific devices. For example, if I want to use the crystal mismatch of two materials, which is part of the defining element of my device. Now, if you go now one step deeper, looking at what are the different techniques on how wafer bonding can be applied, then very broadly we differentiate between two ways how to establish the bonding process. One would be where we actually use the physical and chemical properties of the opposing or the mating surfaces, which we call the direct bonding. where we basically use solid-state interfaces and create a chemical bonding, ultimately a covalent bonding between two surfaces. Or I can use basically a glue. And when I say glue, this could be a glue as you think about it, can be a polymer, but it could also be kind of a metallic glue, or basically using metal layers, either melting metal layers or solid metal layers as my interface. Or I could use what we have here with the glass fluid bonding, basically a glass type paste in order to establish the mechanical connection between my two wafers. And then in the course of my talk, I will discuss some of these technologies here in more detail. Okay, let's start with the very first one, which would be the adhesive bonding. The adhesive bonding, you can think about, there are a lot of thermally curing adhesives, but also thermally curing adhesives have the advantage that they are basically work with all kind of materials, all kind of wafers. But it requires that you have a process step at an elevated temperature, maybe 80 degree, 100 degree, or even higher. So your wafers, your device, or your substrate has to be able to withstand the temperature. If this is not an option, then an UV curing adhesive might be a good alternative. However, you have the limitation in order to enable UV curing, one of the substrates has to be a glass wafer. And very often the challenge is we want to create kind of a cavity, as you see here, I can create directly out of my adhesive the sidewall, so an entire sidewall is my adhesive, or I create a sidewall with micro machining on one wafer, and I have a full layer adhesive film on the other wafer. I might also apply a spray coating techniques, where I can basically conformally coat the micro machine surface, or I can apply a technique where I selectively deposit adhesive on my already established seal rings or side walls of my cavity. So in the course of the presentations for all these techniques, I have kind of this comic-like simplification of the bonding processes. But just to give for comparison reasons, the starting point is I have selectively deposited some polymer lines here. I bring the second wafer into contact. This might or might not be under vacuum or in a specific atmosphere. For example, if you want to have a nitrogen atmosphere inside your cavity or something like this. No? Then the actual bonding, you apply heat and you apply force. When you apply the force, you kind of deform a little bit your polymer. You want to make sure that the polymer is really wetting very well both surfaces so that you have a strong connection. And then after cooling down, your bond is established. Okay, and now I would like to give you a real-world example on why would I want to create some micro-machined cavities with a defined pressure vacuum. So as a starter slide, I have here a couple of applications where this wafer bonding is actually being used. It's actually something for a lot of micro-machined parts. Wafer bonding is a step, so everybody of you in your cell phone, there are multiple devices which are being packaged, which are being created by using the wafer bonding. Examples would be the RF filter, like F-bars, or the inertial sensors, like accelerometers, gyroscopes uses. In some cases, you might have a magnetometer. Pressure sensors, very important for the safety devices in your car. You might create some more esoteric devices like atomic clocks, oscillators, and last but not least, this might also be used in order to make a thermal imager, a so-called bolometer. So on this slide here, I have a very simple cross-section on how a thermal imager does look like. So basically the starting point is as an optical system, you need to have some kind of optics in order to collect infrared light. Which is typically these optics are integrated into your top wafer, and then above you might have, most likely you have some lens system, some beam shaping system. But basically with the wafer bonding, we create a cavity, and in the cavity you have individual pixels. And then on your bottom wafer, the bottom wafer is most likely created by a structured microelectronic system created by CMOS. And basically in order to read out the signals from our individual pixels. The measurement principle is strikingly simple. Basically you have each pixel, so this is in very high vacuum. So if a photon hits your pixel, it basically starts to heat up this pixel. And as we have semiconductors, we can measure the change in the resistance. And that's basically our measurement principle. If a photon hits a pixel, it's being absorbed, it heats up, it increases the temperature of the pixel, increases the resistance, and we have a signal we can detect, or we can basically create an image based on the thermal radiation of our object. The key consideration is here, in order that this has any chance to work, that individual photons, or a small number of photons, create a measurable difference in the temperature, create a measurable difference in the resistance, is that we have to ensure that there's no crosstalk, and the only way to do is to avoid convection in this cavity is if we have a very high vacuum in this cavity. Okay. So now here I have an overview. So the starting point, you can think about this. This would be your wafer with the individual infrared pixels. You have already by micro machining created some sidewalls on next to your imager. But then on your top wafer, you have a cap wafer, and you have the sidewalls. It might be here in this case mentions metal, but it could be also some adhesive or some other material which you want to use for the bonding. You might, by micro machining, enhance your cavity or structure your cavity by some etching process. Then an important point is for most of your devices, you want to ensure that your vacuum in the cavity stays constant basically over the lifetime of the product. Then you have to include a getter material into the cavity. You have the actual bonding process. There's typically another process required in order to activate this getter, which typically means you go to a temperature a little bit higher than the bonding temperature for the activation. And then after the bonding, you have a mechanical, very solid connection, which allows you the further machining, like the dicing, the packaging, but then also for the device, ensures a long lifetime, basically. Okay, now talking a little bit about the sealing of a cavity. So it's on the one hand, we have to deal with the wafer bonding system has to apply a high vacuum. Otherwise, if I don't have a high vacuum to start with, I will never get better. But then we have to deal with, on the one hand, there could be virtual leaks, which from the engineering point of view are kind of very nasty real-world problems. But in your wafer, typically you have certain materials, and you will deal with outgassing phenomena of all kinds. And then you have to think about the quality of your seal ring, specifically permeation of gases or of moisture into your device. So luckily, in most cases, you are primarily concerned about moisture, which are pretty large. Water is quite large molecules. But if you're more concerned about the gas permeation, then you have to go to very good seals. And in order to create a very nice seal, there are three concepts. Typically, the thicker the better. a thicker seal works very well. But this is exactly what in the world of the microstructuring, the world of microelectronics, micro packaging, we don't want to do. We don't want to consume too much material. We don't want to consume too much real estate on your wafer, basically. So in this case, we have to go to better materials, and better materials typically means tighter materials, means going from an adhesive to a metal seal ring. So when we talk about what types of metal seal rings we can apply for in wafer bonding, actually wafer bonding is kind of an dream world for the metallurgists, because here we deal with all kinds of alloys, and we are dealing with it in a very, very pure base. So all the materials here, they are deposited from typically pure, very pure targets. So we can apply all kinds of things which usually are only in the metallurgy textbook. Here in the world of the microengineering, microstructuring, actually this becomes a reality. So this involves we are very frequently dealing with real eutectic compositions where you have two wafers with different alloys, and you have an alloying process. The solid liquid interdiffusion is a kind of a subset of eutectic bonding. I will address in a little bit. All kind of soldering is possible, and there's also the possibility diffusion-based thermocompression bonding. And I will, in the next couple of minutes, I will go into more details about these technologies here. So let's start with the thermocompression bonding. The idea of thermocompression bonding is basically that I use one material, or could be an alloy, and I have the same material on both sides of my wafer, and I want to create a solid permanent contact. Basically the key mechanism, what we're talking about when you bring two metal surfaces into contact, you will always have some kind of diffusion between two surfaces, but you have to ensure that the surfaces are really, really close to each other in order that we have diffusion, metal ion diffusion of any reasonable rate. The materials we are talking about, most common is the gold-gold bonding. For example, for RF filters, gold-gold bonding is being used probably in all of your cell phones. You have some RF filters with gold-gold bonding involved. Aluminum is, I will address aluminum in a little bit in detail. It could also be used, or copper bonding to copper bonding. And as you see here, these bonding methods require a very high temperature, very high in terms of what typically the devices can or want to withstand. We have to go to a higher temperature, means a higher diffusion rate, means a lower cycling. So this is basically the magic. So there is a range, but the temperature is reasonably high for microelectronic devices. However, if your device is able to withstand the temperature, then metal thermocompression bonding provides a lot of nice features. It is conductive, it is hermetic, it's a very good mechanical strength, so all kinds of these drop tests and thermal cycling tests, which are required for all kinds of industrial or consumer-based applications. This stands very easily. You can have a very small, narrow bond lines, meaning you don't consume area on your wafer just for the sidewall. It allows a very good alignment of the two wafers to each other. Specifically, if you're able to use gold, then you don't have to deal with this oxide management issues, which in a lot of cases are the type of problems which keep the engineers awake at night. So let's take a look in a little bit more detail. So here, these two on the left side, these two golden rectangles here should symbolize here my gold interfaces, or let's say in this case probably more copper or interfaces. But in a lot of cases, except when you're using gold, you have to deal with this on your metal. You will have some oxides. Oxides are forming in a lot of cases very rapidly. So in reality, you will always have to think about if you develop a process flow, how to make such a device. Think about if there's an oxide, how can you get rid of it, and how can you get rid of the oxide during the bonding process or very shortly before bonding. In the case of the wafer bonding, typically we flush the surfaces with reactive gas, like forming gas, or you might have a formic acid bubbler in order to reduce the surfaces and get rid of the oxides. And this happens at a starting point of the process, might be room temperature or slightly elevated. Ideally, we are successful. We create oxide-free surfaces, and then we can bring the surfaces into contact, and then we start actually heating up, starting the bonding process and then increase the temperature. Now here an important point is we need, for metal thermocompression bonding, we need very, very flat surfaces. So the wafer bonders, they can technically go to a very high, apply reasonably high pressure in order that you basically, if you have a material, the materials can overcome a little bit. We can flatten out the surfaces a little bit, but the higher your density of your seal rings or so, it becomes very difficult to overcome. If you have a gap in the interface, then basically you have a permeation path, you have a penetration path for gases, for moisture, and you will run into issues with the sealing quality. Right? Okay. So yeah, once we start heating up, basically we start to see metal ion diffusion. Typically the diffusion path is across our grain boundaries, which is kind of the diffusion highway in a metal system. And the engineers typically use this as a means to assess whether the bonding has been good, whether there has been a reasonable enough material transfer from one surface to another, if we actually start to see grain boundary growth across the bonding interface. That basically, if you do an interface cross-section, you would not see this line of the bond interface at all anymore. This would be your way how to determine that you basically have a void-free bonding, that you have a mechanical and also a stable and hermetically hermetic seal ring on your device. So here we see, okay, on this picture here, that's basically what you want to see in your microscope. If you look at the interface, bond interface has disappeared, and you see the nice grain growth across the grain boundary. Yep. And at this point of time, your wafer bond is established. The connection is established. Typically in the system, you cool down the wafer, but cooling itself does not have any impact or any functional component for the wafer bonding process for metal thermocompression bonding. Okay, so here I have again my kind of cartoons. I bring my two wafers in contact. Typically, or in the wafer bonder still, I have to apply some flashing with some oxide removal, forming gas or something, treat the oxide removal. Then I bring my surfaces into contact, I heat them up. I typically apply a very high bond force. And thermocompression bonding is not the fastest process in the world. So typically we are looking here at something like 20-30 minutes bonding process time or even more. And then finally I cool it and I have my nice cavities and the very good metal-based seal rings. Okay, now another very interesting way in comparison to the metal thermocompression bonding would be eutectic bonding. So I think you all have seen in your engineering classes at some point the eutectic diagrams, the phase diagrams. Here we have for a binary alloy like gold silicon, and we want to use this kind of oddity of nature that at a specific stoichiometric composition, the liquidus point is lower than at other stoichiometric compositions. What this means is that basically during the bonding process, again, you start with solid metal surfaces on both sides, but during the bonding, you have a short period of time where actually you create a liquid phase in a liquid metal film, liquid metal phase in your bond interface. What this means is if you have a liquid phase, then it becomes a lot easier to close all the gaps, to fill all the trenches or crevices or whatever you have on your wafer, in order that you create a very nice hermetic seal. So here we see again, I use the same kind of cartoon style demonstration here for the bonding process. So let's assume I have a binary alloy, material A, material B. I bring the two materials into contact. At this point, I have two solid interfaces. But then during the heat up, I already see some kind of this diffusion, metal ion diffusion. And what happens is, as I have this metal ion diffusion, let's jump back. I'm actually moving in my phase diagram from both sides towards a stoichiometric composition where I have my the lower liquidus point. And so what happens is, at some point of time when I have had enough of this metal ion diffusion, and here we basically see the temperature curve in the bonder, and I'm in the bonder, then my entire system is at a temperature higher than my eutectic point. Then basically I start to see some liquid interface, and then I have basically I have a liquid, all my voids, gaps between my seal rings are being closed just by the properties of having a liquid in the interface. And then basically I have to cool down. In this case, the cooling down has to be very accurate, because cooling down a liquid, if this would not be the homogeneous across the entire wafer, it would be very easy to integrate some stress into your device. And especially for a lot of MEMS devices, if you already create a stress by the package, then you probably already create some drift in your sensor. So here cooling is, especially the very first part, going from the liquid phase to the solid phase, is very important for eutectic wafer bonding, that you do it very, 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 very controlled. Okay. Yeah, again, the symbolization, very similar to what we have seen for the metal thermocompression bonding, but the main difference is, in this case, during the bond process, I go shortly through a metal phase, which means with the eutectic bonding, it's a lot easier to deal with gaps in your interface, or in other words, with the metal thermocompression bonding, you have to take a lot more effort in order to avoid having gaps in the interface to start with, having gaps in the interface prior to the bond. Okay, and then another very important process in the world of the microelectromechanical systems or MEMS devices, this is the anodic bond. anodic bonding relies on the property of a glass wafer, or actually it could be a deposited glass film on any kind of wafer. These are specific types of glasses. Typically, they have a very high metal ion content, metal ions of the alkali group. And what basically happens, I bring my two wafers into contact. I go to a very high temperature, typically in the range of 350, 400 degrees C. At this temperature, I will see a thermal dissociation between my metal oxides in the glass. And now I apply a fairly high electric potential here to my through the interface. And what happens here, basically I draw my oxide ions, I draw them into the interface, and basically I kind of have some kind of an internal deposition of the oxide ions in the interface. I grow an oxide layer between my glass wafer and my silicon wafer, and I form a very strong bond. So anodic bonding is being used for very harsh devices like pressure sensors, higher pressure sensors, etc., all this kind. But if you need a super strong interface, then anodic bonding is definitely one of the good candidates, because the bond interface, due to because we have this migration of the oxide ions into the interface, and they create a strong and I create an oxide layer in interface, I grow a really strong mechanical contact between my two wafers. Okay, and now coming from the world of the microelectromechanical system, the second example I wanted to show you. This is more from the microelectronics world, from the more the high-end devices in the microelectronics. As an example, I have here the backside illuminated image sensors, but then I will also draw the connection to some of the newest generations of CPUs, GPUs. So in semiconductor manufacturing, I have the situation that in order to create a diode or a transistor, I need to implant selected areas with my dopants, and then I have to activate the dopants at a very high temperature. And the temperature required for the dopant activation is higher than the temperature what later on the metals could withstand. So the metal is a natural enemy of a semiconductor. I need it in order to as a means to transfer the electricity in and out, the signals in and out, but I cannot have them in my transistor area. So what this means is, in every semiconductor in the world, you first have to create your transistors, and then later on you deposit on top your metals. And in order to contain these metals on where you want them to be, there are these diffusion barriers, and the diffusion barriers basically would break down the temperature required for implantation. Okay, and long story short, what this means, you always have to create the transistor first, and then you deposit the metal later on. Now, if you think about an image sensor, this has now a very unfortunate situation that basically you can create image sensor, basically you create photodiodes on your wafer, and then you create just a metal grid on top, and the metal grid would shade a big portion of your photodiodes. And what this means is basically that either you have to go to larger pixel area, or you lose some sensitivity based to this internal shading. And now the very simple trick which has been applied for the so-called backside illuminated image sensors is basically I take my I build in manufacturing, I build up photodiodes first, and then a metal grid on top, but then basically I just want to flip around my entire stack, which is usually not so easy, because when I flip around my entire stack, I would have the full silicon metal, full silicon wafer below. I would have 700 micron of silicon, and then of course I cannot look through. So here's the process flow and how this is actually applied, and it's you'll see there are a couple of wafer bonding steps. So the first block here in blue, this is the standard semiconductor processing, CMOS processing, semiconductor processing. I create my photodiodes on my wafer. Photodiodes plus the metallization on top. And then I basically, the trick I apply is I use a wafer bonding step. So I bond this surface to another silicon wafer. And then I flip around my wafer, and I can remove all the original silicon. I can remove. So in the microelectronics world, typically what happens, the wafer is very thick, 750, 775 micron thick, but the device itself is typically less than a micron. So the entire thickness of the wafer, the whole purpose is that the wafer does not break during manufacturing, but most of the silicon is actually unused and is being removed at some point later in the processing. And that's what we're doing here. After this bond process, I remove my entire silicon by a grinding, by an etching step. And then now I have basically from revealed my photodiodes. Nothing is blocking the path of light to my photodiodes. I create my color filters. I put some micro lenses on it, and then of course I have some optical system on top. And the trick we are basically applying here, or the process we are using, this is a so-called fusion bonding process. We are using oxide layers, oxide films on both wafers. These oxide films are planarized, so I apply a process called chemical mechanical polishing to have super flat surfaces. And then I basically, once I have oxide layers on both wafers, I can have a very simple, easy bond process. It's void-free, it's very high alignment, it's very fast. So technically speaking, I basically have, if I can create oxide layers and if I can planarize oxide layers on both wafers, then I can use this fusion bonding in order to bond any kind of wafers, any kind of devices, and connect them permanently. Just some trivia. Basically, this fusion bonding first was described by Galileo Galilei already 400 years, nearly 400 years ago. You probably know this phenomenon. If you have two microscope sliders and you have a droplet of water in between and you press these two sliders together, it's very difficult to pull them apart. And this force, what you are feeling here, this is already an example of the fusion bonding. In the microelectronics world, this process has been used for many years. For example, all these so-called silicon and insulator wafers, where a lot of today's devices are being created on. They are starting with the wafer bonding, fusion bonding process in the wafer manufacturing. So here I have how is, in a little bit more detail, how is wafer bonding or fusion bonding applied. I have my two wafers. I have to ensure that I have really super clean surfaces. So any particle in the interface will create a defect, will create a large defect. So this is really a semiconductor fab process with front-end cleanliness required. Then there's a plasma activation step, and then finally the bonding, and the bonding actually happens at room temperature. Here on this slide, what I wanted to show, even after chemical mechanical polishing, even if you have probably the flattest surfaces in the world you can think about, if you bring the two wafers in contact, you will still have gaps in the interface. And in order to close this gap, we are basically applying a trick. We have a so-called plasma activation, which means that we are disturbing the crystallographic structure of our interfaces. We are kind of enhancing the entropy here in my system. and then with a very moderate annealing temperature, I can start a recrystallization or reorientation of my crystal lattices, of my oxide layers, and I basically get a gap filling. And also with fusion bonding, we are able to achieve bond interfaces without any gaps, without any voids. Yeah. So the bonding itself happens at room temperature. Initially, I create some hydrogen bridge bonding, but during the annealing process, this is being transferred into a full area covalent bond between the two wafers. Now, this can be used for any kind of materials, any kind of wafers or semiconductors. I can integrate by fusion bonding. So as long as I have a dielectric, if I can deposit a dielectric on a wafer and if I'm able to polish it very well, that I can use this to transfer layers of one semiconductor to another. Here we see an example of an indium gallium arsenide transferred onto a silicon, but it can be used for all kind of materials. And for those of you who are interested in the microelectronics, if you look at the roadmaps of the next generation of transistors, you will see that in a couple of years for the leading edge transistors, we will see more of this integration of different semiconductor materials into the transistors, and then probably in roughly 10 years or so, a transfer of 2D materials like graphene, also used for transistors. And also here, this transfer of the 2D materials would apply a wafer bonding process. And then last but not least, one word. One of the buzzwords in the microelectronics today is the hybrid bonding. Hybrid bonding basically combines what I have presented you today in this lecture. You see here in this interface is the blue areas. These are my dielectrics, are my oxides, where I create a fusion bond. I first have a fusion bond process, and then during the annealing process, I apply the trick that basically my metal ion has a larger thermal expansion than my oxides. So then the metals kind of grow into each other, and I kind of have, you can even think of it like some internal welding. Yeah? So hybrid bonding describes the simultaneous creation of a mechanical interface and of an electrical conductive interface between my two wafers. Okay, and then, okay, on this slide, I just have a wafer bonding is being used for a lot of things. A lot of your electronic components of your cell phone use it today, and it's actually quite a versatile method. So to summarize, it's established very well in high volume manufacturing. So thousands of bonds every hour around the world, either for encapsulation of a cavity or for integration for the permanent connection on the micro level of two or more different devices. And yeah, in the lecture today, I wanted to give you a little bit of an overview of how the basics of the engineering are applied here for the microsystem engineering, where we have the chemistry and the physics of the adhesive bonding, all kind of the metallurgical and alloying processes, but also here the fusion bonding. Okay, so I think that this would be the end of my lecture for today. So if you have any questions, I'm more than happy to answer this.
Thank you very much, Thorsten.
Thank you very much.
It was an amazing journey through all the different, well, not all the different, but some of the key bonding techniques. And I just say to the audience here that bonding is a lot more than just sticky tape and super glue. What you've seen there is really critical to being able to actually make devices rather than things that fall apart in application. and you simply don't often have devices without these capabilities. Bonding can be extremely challenging. It's not a trivial part of fabrication, and so getting a talk like this from Thorsten, we're really privileged, Thorsten, to have your knowledge coming to the school like this,
My pleasure, my honor.
and again for you staying up late to be able to do it for us. So we're very grateful. You know, I just want to plug again EVG a little bit, because Thorsten was true to the brief, which is to talk about the technology and the capabilities, and he resisted the urge to, you know, as industry would, to talk about EVG. But EVG is really a great partner, and you can see the kinds of capabilities and knowledge that they've got that they bring to microfabrication engineering. Any questions from the audience, please, or from the chat for those online? I won't let you get away without asking at least one. So who is it going to be? Yes, Dong Hoon.
Can you hear me?
Can you hear Dong Hoon?
Yes, I can hear you.
Would you tell us about QA techniques used in bonding of especially non-transparent substrates like silicon to silicon fusion bonding or direct bonding? And after bonding, how do you assess the quality of bonding? What techniques are available?
Okay. So there are various methods. So typically the simplest what you apply in case that your wafers are transparent to infrared light, then you would basically just look at infrared light through the interface, and pretty much any gap in the interface would create some Newton fringes. You would see it as a contrast variation. If you want to go in more smaller scale, acoustic imaging is a very good method. So you have a scanning acoustic microscope. You can use this in order to detect very accurately if there are any gaps in the interface. The actual question on measuring the bond force, unfortunately, at this point of time, bond force measurement is still a destructive method. Yeah? So it's we are using the techniques to figure or to look at whether there is a gap in the interface, whether there is a void. But actually measuring the bond strength, this is a destructive method. But the good thing is, especially when you talk about the fusion bonding, the technology of creating, or the repeatability of creating the oxide films is very, very high. So the variation from wafer to wafer is actually very low. So in practical terms for fusion bonding, it's very much you might either have some kind of catastrophic failures, like if you have particles in the interface which prevent the two surfaces getting into contact. But if it's bonded, then typically the bond strength will be very high. So our customers usually don't need to test bond strengths then very often, but they all inspect the interfaces for gaps.
Okay, thanks for that question, Dong Hoon. There's a question up the back. That's Mike, isn't it?
Yeah, Mike.
You're in the dark back there.
Hi, Thorsten, can you hear me?
Yes, I can hear you.
Yes. Regarding to the direct wafer bonding, that you write down that you do an annealing process after the bonding, so that annealing temperature, I think, do you suggest is the melting point of the oxidized or a little bit higher than oxidized?
Okay. So there are basically two classes. If you talk about the let's say the wavering, for silicon and insulator wafers, you actually apply what you described. You go above the it's basically a temperature regime in a range of 1000 degrees C. It's what we call a viscous flow in the interfaces, which allows you to basically, due to this viscous flow, get rid of all the voids in the interface. Now, if you have already some microelectronic structures, if you have already transistors, then of course these, especially also the metallization, that would not be able to withstand this 1000 degrees C. And in this case, we have to, or we do, apply this plasma activation, which disturbs our, allows us to do a recrystallization already starting somewhere in the 200 degree range. Most of the devices are being annealed at 300, 350 degrees C, which is well below where your diffusion barriers for your metal lines can very well withstand, so standard temperatures, pretty much.
Okay, thank you, Mike. Thanks again, Thorsten. We are out of time, so I'm going to keep us moving, but please, together with me, let's thank Thorsten again for this wonderful presentation.
My pleasure to be here.
And Thorsten, I think you're actually the host at the moment, so when you get off, don't shut the meeting. Can you give the host back to Bell?
Oh.
Yeah, just make sure. I think you're in charge at the moment. I'll see if... Oh, yeah, that's perfect. I'm the host now. Thank you very much.
Okay.
You're free to have some sleep now. Thanks again. Okay. Are your presentations open already? No. Oh, okay. I'll let you do that while I introduce you. Yeah. Okay. The next two speakers tag team today. Talking to us about packaging. So we've heard a bit about bonding, but there are other elements of putting together devices that are really important to get them to be a product or a fully functional device. As I mentioned before, we've got Barak and Coco joining us today from DSTG, great friends of the facility. Thank you so much for everything that you do through the winter school and through the collaboration that we have. They have some outstanding knowledge and capabilities at DST, as you would imagine. And today, again, we're going to be hearing about packaging. I'll just quickly introduce. This is good with multitasking.
Yep.
You're doing the videos.
I think we got it.
Barak commenced her role at DST in 2019 as a microfabrication specialist. Barak, over here, just in case you didn't already know. And her professional portfolio includes more than 10 years of combined research and industry experience with micro and nano environments. Barak completed her Master of Engineering and PhD degrees at RMIT University, and prior to DSTG, Barak worked as a project engineer at Minifab, which is a leading micro device company in Australia, but has recently been bought out by Schott, which gives you an idea of how fantastic they are. Providing custom development and manufacture of disposable polymer microfluidic based medical devices and life science research devices. And I'll introduce Coco as well so you can seamlessly move between you without me interrupting. So Coco completed her Bachelor of Science with Honours in Materials Science at the University of New South Wales in 2020 and joined the Micro and Nano Engineering team at DSTG in 2021. As a microfabrication specialist, Coco's experience includes photolithography, micropackaging techniques such as wire bonding, decapsulation and wafer dicing, and Coco has used the ANFF facilities in what she's doing, and again, working very closely across the two sites. So, I've said enough, so I'll hand over to you. Thank you.
Yeah.
Is it?
It should be working.
Oh, looks good. Okay.
Yeah, thanks, Craig. So, as Craig introduced us, Dr. Brad Korzynski and Coco Kennedy. If you can't remember my name, my colleagues call me BK and Max Coco CK. We work at micro and nano engineering discipline within research engineering branch at the DSTG. So integrated circuitry manufacturing is incredibly important industry in today's world. So our daily lives revolve around the use of these devices, and that wouldn't be possible without integrated circuits. So these integrated circuits must be housed in a package that enables their functionalities such as mechanical stability, environmental protection, electrical connection, and thermal management. And so this IC is a collection of electronic components such as resistors, capacitors, transistors in one tiny chip. So what is a package? Package is a case that protects the circuit material from physical damage or the corrosion. So the packaging is the final stage of the semiconductor device fabrication. So on the right-hand side, here in this flow chart you can see, on Tuesday our colleague Mariam talked about photolithography. So you can design lots of hundreds of chips in one wafer. Depends on your design, depends on the size of your wafer. So, however, we need to pick this individual chips from this wafer. So we need to dice this wafer, and then we need to individually pick the chip, and then we need to make sure there's an electrical connection from the chip to the terminals. So we need wire bonding. And then the last stage of the packaging is encapsulating, because your whole design, the package, it has to be protected from physical damage. So just in case your colleagues might sit on your the samples, if it's sitting on your desk unattended. So in today's lecture, we'll cover wafer dicing and wire bonding, encapsulation and decapsulation.
Okay, thank you, Barak. So as Barak said, when you have a wafer, and during the winter school you've learnt a lot about the processes that are involved with making devices. You've got photolithography, etching, deposition, and also wafer bonding. These are all the processes that make up your final device. And as Barak said, the start of the final steps with packaging starts with dicing. You have potentially hundreds of devices on one wafer, and we need to separate these out. So we do that by dicing. And there are a few different methods of dicing. This depends on what your wafer material is made of and how dense the actual devices are on that wafer. So a couple of the common methods are listed here. You should have learnt already about laser ablation and laser milling in Dr. Ben Johnson's lecture, I believe, on Wednesday, so I'm not going to go over that. But I will talk about blade dicing, which is very common, and I'll also briefly talk about stealth dicing. So blade dicing is a common technique, especially for smaller research scale applications. And this is what we use at DSTG, and this is also what is used at ANFF-SA at UniSA. So in the blade dicing method, a diamond impregnated blade is used, very similar to how you might think of a circular saw, to dice up your wafer into individual die. So how this is done is the wafer is attached to adhesive tape, which is mounted on a frame, and then this frame is aligned in your wafer dicer. You can program your machine to dice down your dicing streets, which is basically just the distance between your individual devices. It will dice first in one direction, and for most applications you have square or rectangular chips, so you will rotate by 90 degrees and then dice again in the other direction. And so there are quite a few benefits to using this blade dicing method. It can cut relatively deep in terms of microfabrication. 1 millimeter thick wafer can be thought of as quite thick. It's very accurate, especially with these new automatic dicing machines. It's very repeatable as well. And it has a low running cost, which makes it very useful for research scale. So your only real consumable here is the blades themselves if you look after your machine properly. So you can see here in this diagram down the bottom here, the usual way that we dice is we want to cut through 100% of the wafer and just into a small percentage of that dicing tape, and this is what makes it really easy for us to remove those devices after dicing. So I'm going to talk a little bit now about the optimization of the actual dicing process. So obviously our number one objective when we are dicing is to cut nice and straight so we get really nice dies with minimum chipping and no heat damage. Secondary to that is we also want to protect our blade so that we can use it over and over again and reduce the running cost of the machine. So as I mentioned, this is a physical technique using a diamond impregnated blade, so there's a lot of frictional heat generated in this process. This means that there has to be a water jet running which is directed at the interface of the blade and the wafer at all times. And this also helps with the removal of any debris that's generated during dicing. So there are a few things that we have to consider to optimise this process, and the properties of the blade that we choose is going to depend on the material that is being cut. So, and also the patterning of the devices on that wafer. So the thickness of our wafer is going to determine the diameter of the blade that we need to use, and the street width is going to determine the width of the blade that we need to use. So generally, you need to account for your kerf width being double the width of your blade, and your street width needs to be a little bit wider than that to account for any chipping. If you choose your parameters correctly, chipping should be kept to an absolute minimum. Also to consider on the blade is the grit, so the size and the concentration of the diamond particles that you have in that blade. So for very hard materials like ceramics, alumina, stuff like that, you need larger diamond particles to really cut through that material. This also means that material is being moved at a greater rate, so you can actually use a higher feed speed, which is the speed at which the blade moves over the material. This can also to consider is the actual RPM of the blade. Generally, with these wafer dicing techniques, you're using between 10 and 60,000 RPM, but again, that depends on your material. So we've talked about large grit, that's good for very hard materials, but the smaller your grit is, you're going to get a very smooth sidewall in your dicing and reduced chipping. So it is always a balance between how quickly you can dice your material and what kind of finish you want. So the blade parameters that we have is also going to influence the operation conditions. As I said, the feed speed depends on your concentration of the grit in your blade, and the rotation speed as well depends on your material. The blade height, again, is influenced by the thickness of your material. You want to cut through 100% of the wafer and just a small percentage of the tape. And as well, you want your water jet conditions to be optimum so that the blade is being kept cool as well as the wafer itself. Now, one thing I haven't mentioned yet, you can see on the right-hand side there, I've got a picture of some alignment marks. You should remember this from Mariam's lecture on Tuesday, that in the photolithography step, alignment marks are very crucial for subsequent exposures, for making sure that your pattern is being kept in the correct alignment. This is also really crucial for dicing, as it helps us make sure that the cuts is being made in the centre of the street and we're not going to encroach on the circuit, even if there is a small amount of chipping. So the better your alignment marks are in your photolithography and design steps, it's also going to help you get a really good result when you're dicing. So that's something to keep in mind, is that procedure continues on. So now I just have a short video which shows the premise of stealth dicing. So it starts off in a very similar way, where you will have your wafer attached to some dicing tape. But this actually uses an internally focused laser. So it's cutting down the streets just in the same manner as the blade dicing, but it actually makes a modified internal layer of micro cracks. This means that when we expand the tape in every direction equally, these micro cracks are able to propagate, and it forms really nice smooth dicing lines. This is really good because there's no heat damage here. It's also a lot faster than blade dicing, but it is extremely expensive. So for a commercial application, this would be more common than blade dicing, but not what we use on a small scale. I'll pass over to Barak.
Thanks, Joko, for dicing the wafer for me. So far we've been handling with a big like the 4-inch, 6-inch, or 8-inch wafer. So and then this wafer is placed on a frame with a dicing tape. However, now that's this type. We need to pick this. You can see in the monitor in this image. We need to pick one of these dies individually. So we, from our experience, we used to pick this individual dies manually. However, this process can be very challenging because the dies are very small, and also it can be time consuming because these dies are really stuck onto the dicing tape, and we can physically damage these chips. And also, while you're taking this out, from our experience, again, you can lose these chips. They can flake and go on the laboratory anyway. So, because of this experience, we purchased the pick and place system. In other words, this is a die sorter, if you like to Google it. This is a semi-automated system. Basically, you place your dice wafer with the frame on the stage here, and there is a needle underneath, and comes and lifts this the desired die from underneath and peers through the dicing tape, releases the surface tension, and there's an arm here, goes on top of that chip and goes on top of it, picks it by the help of vacuum, and takes back to desired location. It could be your gel pack, could be your petri dish. So after here, picks it up. So we have the surface contact and non-surface contact operation. So these are like on the top image, you can see this is a vacuum tube. So if you're not really worried about your design, like if you don't have a bridges like gas or GAN chips, you can use a vacuum tube. But if you're worried about your design, you've got very fragile features on top on your chip, so you can use like this image non-surface contact the tip. So basically, here from the wafer holder, you take your chip, take it here, and there are two microscopes here. So one is for the side infection, one is for the underside inspection. So you can clearly see your chip is damaged during this damage or not during this process. So either at this stage, you're about to either reject your chip if it's damaged, and if it's not damaged, you can continue the step and it can go onto the desired location in gel pack. And also there's a reverse operation here as well. You might have your chips in the gel pack, so we have another holder. It goes on to, you can place it here on gel pack, and the similar process, the vacuum and the tip comes, the arm comes and picks it and takes it to another desired location. So we have our die, individual die, and now we've got our printed circuit board or any desired substrate, and we need to place our individual die on top of the substrate. How do we do it? So we place either conductive or non-conductive epoxy, drop off the epoxy on the substrate, and then the die, we place the die on top of it carefully, and we put this in the oven to cure it. So we follow the instructions for the data sheet, depends on the epoxy we are using. So the next step, so we cured our die on the substrate and is physically attached to the substrate, and then we need to make sure there's an electrical connection from our chip to the terminals. So the most common technique is wire bonding technique. So wire bonding is a standard interconnection technique that enables electrical connections from microchips to the terminals. So wire bonding is categorized by the bonding method. So first technique I will talk about is ball wedge bonding, and we generally call it ball bonding. So what happens is here, so you have your, in the first step, you have your capillary. So you feed your wire through the capillary. So there's an electrical flame off, and this electrical spark, and it creates a free air ball. You can see in the second step. So basically what happened in the second step is this melts the wire, and due to the surface tension creates this free air ball. Then capillary, in the third step, the capillary moves towards the first target. So creating your first bond with the ball shape on the first target. And then starts creating the capillary, your bonding equipment starts moving towards the second target and creating a loop shape. And here, and then capillary crash, by applying, sorry, I forgot to mention the third step. So you apply ultrasonic energy and heat as your forces, and then creates this first ball. And then the second one, when you come to under same forces, you create your second bond, and while the clamp closes, the bonding tool goes upwards and creates your wedge bonding here, and creates leaves the tip here for your wire for the next bond. So wedge bonding is slightly different. The wedge bonding tool is slightly different than the ball bonding equipment. So the most obvious difference is your bonding tool, which is the bonding capillary, which resembles a very fine, you can see here, very fine pointed stamp. So a similar application very similarly to comparing to the ball bonding, and the bonding equipment reaches to first target, and then under the applying ultrasonic energy and creates the first wedge. And then the bonding equipment move towards the second target and creating a loop and applying ultrasonic energy again, and creates the second wedge. And then the bonding tool moves upwards. So these two techniques have advantages and disadvantages. However, the bonding method is decided by your application. So you can clearly see in this image, in this video, how the ball bonding is created. And applying heat and ultrasonic energy creates the first bond, creates the loop, and the capillary is moving towards the second target. And then we are about to create our second, I think it's a bit glitchy, sorry about that. Creates the second bond under the heat and ultrasonic energy. And the clamp close and tears the wire. And creates again, you can clearly see electrical flame up, creates the ball for the next bond. So these are the images of scanning electron microscopy techniques applied to capture these images. You can, on the left-hand side, you can see the ball bonding, and on the right-hand side, you can see the wedge bonding close up. And reverse bonding. So why do we need reverse bonding? In order to have a stable wire bond, in some circumstances we need to do reverse bonding. Generally, wire bonding is considered as forward bonding. However, a chip like you can see in this image, a chip like a very high chip from the substrate you might need to have a control of the angle of your wire, and you might need to have a longer wire loop. So in this case, the reverse bonding is required. So in my experience, I had a similar chip, like 1 millimeter high chip, and I tried to do forward bonding. However, the wire hit the edge of the chip, and this caused the break in the wire. So if we do reverse, so we have a stable wire bond. So what do we have at DSTG as a wire bonder? So we have manual wire bonders, and also we have automatic wire bonder. So when I started DSTG, we only had 58 series FNS bonding, one of them. Now we have two of them, and we have changeable bond heads. So this machine is capable of manual and automatic bond, and you can have one wire per second. So the top one is the ball bonder. We have two wedge bonder, depends on the size of your wire, and we have heavy wire bond heads. And also at the bottom you can see a little image, and this machine is capable of doing multi-wire the programming. So what happens is you program, you can see on the screen, you can see that there's the microscope there, and you can program your wire bonder to do, like, it could be hundreds of wire bonds. And this might take a little bit time, because when you say automatic wire bonder, it might sound like, oh, it's straightforward. However, this programming takes a little while. But when it's programmed, you push one button, start, and it does the job. So this is the video of the our wire bonder. So you can say this is a wedge bonding with the aluminium wire. So obviously this has been programmed, and you can see how quick this is after it's programmed, and bondable, changeable bond heads, very straightforward. You just need to calibrate after you change your the bond head. You can either inspect through the microscope or through your monitor. And also, this is the example of some of the applications. We don't do it, but however, like, this is part of the FNS bond deck, so you can do battery bonding. So another capability we have at the STG is flip chip bonding. So flip chip bonding is another micro packaging technology, the bonding technology. So in the top image you can see there's your die, and you have perfect spheres on the pads of your chip. So then you flip your chip and take onto the substrate and put on the place on top of the corresponding pads with the substrate, and then apply heat. So this can be on the heated stage, or this bumps, solder bumps can be cured in the oven. So here on the left-hand side, you see a flip chip bonding system. So basically there's a vacuum stage, there's your flip chip, and there's a substrate with the gold bumps on it, and there's the heat stage. So there are stages. So what happened here is your flip chip is picked up by the vacuum tool and then placed onto the substrate on top of the gold corresponding contacts under controlled force and heated through, and these bumps are cured. So there are, and also during this stage, when it's placed controllably with the force, the ultrasonic vibration propagates through your chip, and the three main factors play in the flip chip, which is direct force, controlled direct force, ultrasonic energy, and the heat. And now your chip is decued, and the flip chip is bonded. So, so how do we test these wire bonds? Before I go into wire bonding testing method, so the more important part is like your material. So in the ball bonding and wedge bonding slides you saw, basically we use wires. So we generally use wires from 17 micron to like a 50 micron at the moment. Depends on our applications. So the gold and aluminium wire, they're 25 micron diameter, and generally in the past the copper wire has been used. So you have your design, you have die, and depends on the fabrication process, you choose your wire materials. And also the substrate, your printed circuit board is really playing a role in the metallization of this printed circuit boards are really crucial, because you need a reliable and stable bonding, very strong bond from your chip to the printed circuit board, and you have to consider when you're designing your PCB or purchasing your PCB, you have to reconsider this. And also the pad size is really important, because you don't want your bond size to be bigger than the pad size on the substrate or on your chip. So we did the wire bonding. How do we test this? You need a special equipment that has a special hook and goes, and you need to test the strength and the quality of your wire. So basically in the bottom image you can see, so this is our first bond and second bond, and then the force will be applied with the hook upwards. So this, if the bonds are equally strong, so the wire should break from the middle here. So you can see on the right side of the image the schematic of wire pull test. So in like these are the failure modes. So you want the wire to break from here. That it means equally these bonds are strong. Then after we did our wire bonding, we did our tests, we specified our parameters. So the final stage is encapsulating this wire bonded the sample. So to protect from the physical damage or the corrosion as mentioned in the previous slides. So generally epoxies like thermally conductive or the electroconductive epoxies are used, and in some cases we use, generally we use ultraviolet curable materials, which you can put a blob of polymer like the UV curable material on top of your sample in order to cover all the connections, interconnections. Then you put in the oven, in the UV curable box, and then it solidifies under the UV.
Okay, well, thanks, Brack, for encapsulating that package, but unfortunately I'm going to want to decapsulate that now. And one of the reasons you might want to do that is for failure analysis, but also for quality assurance as well. For example, if you put a device into use and it's not working, one of the wire bonds may have unfortunately used while the epoxy was curing or something like that. So you can see some images of decapsulated chips here, and there's a couple of different methods that can be used, but for the sake of time I'm going to talk about chemical jet etching only. So the first step before we jet etch is to X-ray our package. And this is useful. It shows us the location and the size of our chip within the package. But we can also see some wire bonds here too if you look closely, especially if you have a high resolution X-ray. So if you can see that some of these wire bonds are already broken, it means that during the jet etching process, you can actually just decapsulate a specific area and just focus on where that failure has occurred. So I'll just finish off by showing a schematic of a jet etching machine. The main things to take away from this diagram is that your package is placed upside down at the top of the diagram there, and then you have a chemically resistant rubber mask that you have designed based on what you see in your X-ray, so that the only part of the package that is exposed to acid is the part that you actually want to see. So with jet etching, we generally use two different types of acid depending on what the package has been encapsulated with, which type of polymer, and that is fuming nitric and also sulfuric acid. So how this works is we can program this machine to heat a specific volume of acid over a specific period of time to a specific temperature and expose our package to that acid, which will generally gradually react with that polymer surface and expose our dye. Then our package will go through subsequent cleaning stages, and we can assess under the microscope whether or not we need to do further decapsulation or whether that is sufficient enough for our testing. And at this point, if some wire bonds are also exposed, we can go back and do wire bond pool testing as well for quality assurance. It's worth noting here too that with these jet etching machines, they're completely encapsulated themselves, so there is no actual contact between the operator and any acid, so they are very safe machines there too. So just finishing up quickly in the interest of time, I'd like to thank ANFF-SA for hosting the Microengineering School. DSTG is always very happy to be involved. So thank you very much, and we'll take any questions if there's time.
Wonderful presentation, very interesting, and I always think of it as therapy for microfabrication people to watch these wire bonds just so delicately be placed so beautifully and easily and quickly. So are there questions from Prof and Barry? Let's see if we can get one question. I know you'll want to go to morning tea. Yes?
What's the smallest die that you're currently working with as a research perspective?
At the moment, the height, I think 50 micron, and 50 micron thickness, the smallest one, and generally 1 by 1 millimeter. So it's very, so you need to get tweezers and handle it, and you must scratch on top of it. That's the reason we purchased the pick and place system. Then you can have a control of the not damaging your chip, the small ones with a tweezer.
Don't drink coffee or you'll have shaky hands. It ruins everything.
Okay, well, thank you for the question. Please ask more questions over morning tea. I just have a gift for both of you. I don't know if there's a difference between orange and red, but if there is, you can swap.
Thank you.
Thank you very much.
Thank you.
Let's thank them again. Let's come back at o'clock sharp to start the next presentation. Just because I want to give you a chance to have some tea and coffee, okay? Okay, welcome back everyone. Thanks for moving so quickly from morning tea back to the main room. We have two, and our last two, I'm expecting everyone to go, oh, last two. Last two insight talks this morning, and then you go into the pracs this afternoon. The first insight talk is from Stephen Blackney. Stephen's based at Flinders University, I mentioned that earlier today, and spends time at the Mawson Lakes campus of UniSA as well in the ANFF node, so working across the two nodes, but also part of the medical device partnering program. So he joined the MDPP in 2019 after roles within the Department for Trade and Investment at the Government of South Australia and medical device cluster organisation MedTech South Australia. He led a South Australian health and life sciences trade mission to China in 2018 And he started his career as a mechanical design engineer, and I think there would be some of those in the audience today, working for medical device companies in Australia and the UK. And there's been an increased investment in what's happening within ANFF at Flinders Uni. But Stephen's going to tell you about the Medical Device Partnering Program as a highly successful industry engagement for the capabilities that are on campus there. So Stephen, I'll hand over to you. Thank you very much for joining us.
Thanks, everyone. So I thought I'd just start by asking whether anyone is involved in the medical device space at all. Any hands? I know at least one does, so... Okay, so I thought what I'll do, I'll talk a little bit about our programme and how we've been helping medical device companies, but then I'll talk a little bit about some of the regulatory and quality requirements, but not in too much detail, but more to explain some of the future plans for MDPP. So thanks for the introduction. I think Craig did a better job than I could do. So I'll play you a short video just as an intro. Hopefully the sound works okay.
Early stage innovation and technology development. It might be that someone just has a concept for a new medical device. It might be that they've got an early stage prototype. And the role that we play is connecting all of the pieces of the puzzle.
Currently, especially in breast cancer cases, they have no way of determining during the surgery whether or not they've removed the entire tumour. So effectively what happens is in between 15 and 20% of cases, the patient has to go in for a follow-up surgery.
Emotionally, it's something of a roller coaster. Because I had to have second surgery, the time before I could start having chemotherapy and finally radiotherapy, both of those had to be delayed. And you know all through this that time is of the essence.
So the need that was identified was a tool that could actually be used in theatre to be able to measure to see whether or not the entire tumour had been removed. So what we had developed here was a probe that can actually look at the surface of the tissue. So simply by placing the probe in contact with the surface and doing a measurement, you can actually tell whether or not the place you're in contact with is healthy or cancerous. The MDPP was involved in both developing some of the sampling hardware that we use. So they talked to some of the surgeons and some of the end users to try and develop this. So what they gave to us was a prototype of the device, as well as actually doing some market research to have a look to see what sort of needs were out there, what were the competing technologies, and how did our device fit into all of this.
So from a researcher's perspective, the best part of the NDPP is being able to really direct or provide some really critical insight to an idea or a theme. The medical device partnering program is fantastic because it gives you an opportunity to be involved in possible product development or prototype development. So at that leading edge of where an idea might be coming from an idea into something tangible and having lots of input, which brings so much experience to the table as well. And you can have multiple experts from multiple domains looking at your idea from all of their different perspectives. So it can be mathematicians or engineers or designers and end users, people who might use it and people who might make it for you as well. It's even hard to describe how valuable that is to someone who's just got an idea and who wants to move it forward.
I was looking for ways of collaborating on these projects to try and commercialise some of the ideas that I was having through my work as a registered nurse. We've needed 3D printing, engineering support. There's a lot of complexities. It also gave us access to academic staff, which we needed, because we were looking for proof of concept. So we sat down and they really critiqued the project to sort of look at some of the things I hadn't considered, some of the commercial aspects, some of the manufacturing aspects.
And actually, it's not just research for research's sake, it's actually research that will help develop ideas, but ultimately help to benefit patients. So it really is focused about improving clinical outcomes, improving quality and safety, and making something efficient and making something work.
It would have made such a difference to me and all the women I met while I was going through treatment to have had something like this that would have allowed us to just have one surgery. Just a few weeks can make an enormous difference. We just need as many tools in the toolkit to deal with cancer as we can possibly get.
The MDPP was able to provide market support research, which were critical to actually being able to get this device to the point that it's at the moment.
So then that video is good just to give a bit of context on some of the people that we work with and to show that, it's having real-world effects. And a lot of the people who do come are typically clinicians. So Really, MDPP, its initial vision was to make Australia the fastest place in the world to take an idea for a medical device from the idea stage all the way through to having a product on the market. So we started just over 14 years ago, and really a process has developed over that time, which is quite structured now. But what we're offering for applicants is 250 hours of technical expertise, and we do a 30-hour market report. So the technical element is often sort of proof of concept or prototyping type work. Sometimes it's small-scale user trials. And really what we found was that we had clinicians who'd come to us and they'd have an idea for a medical device. They don't have the engineering expertise. They also don't have the business expertise. So one of the things we also have added over time is 30 hours of market assessment. And really that's our way. So we get clinicians who say, all my mates think this is a really great idea. And what we want to be able to do is actually talk to end users and to be able to capture that and put it in an independent document. So often the work that we do, so although I say it's clinicians, often it is researchers as well, usually with some sort of clinical link. And most of the time after they finished a project with us, they go to apply for a government, more of a sort of commercialisation grant. So we wanted to be able to provide a document that would help to sort of validate the market opportunity as well as being able to provide some technical proof of concept to show that the idea would work. And the reason that the program's been very successful is that we, that 250 hours of work that we do, we don't try and keep any of the IP, and we have tried to remove ourselves as much as possible from, which is, again, very similar to the ANFF model, from some of the logistical issues that you might have from working within your university, so we can be much more quick and responsive to some of the needs. So all of the IP that we create in our projects we hand over, including if there's something that could be patented. And all we ask in return is $5,000 as a co-contribution plus any consumables that might be on top of that. So as Craig sort of alluded to, this model's been running for 15 years, and more recently we've had funding through ANFF to set up a medical device prototyping facility, which gives us more equipment to be able to do. So whereas before we've done a lot of manual prototyping, it gives us the ability to do more than one device. So often we get people who at the end of a project sort of want 3 to 5 devices, and now we're able to do that. So I won't go through the process in too much detail, but just quickly, so we have this screening phase. So firstly, people who have an idea come to our website, submit their idea. We'll do our initial screening, just sanity check. I think Professor Karen Reynolds calls it the sniff test, make sure it's sensible. One of the most valuable steps in our process is a workshop, and this is where, whoever it is that's come with an idea, what we'll do is try and get, for example, manufacturers, might be regulatory consultants, it might be a patent attorney, tailor-made to the project. In the case where a researcher has come to us, what we'll do is find 2 or 3 clinicians in that space that not only are able to contribute through that workshop, but may also then go on to be a key opinion leader for the company. We're very lucky the program's been running a long time, so we have very good links into the clinical community. So we're actually, where companies may struggle, we're really able to get some very valuable people. And we've had companies that haven't gone on to do the 250-hour project with us, but off the back of the workshop have created a company. Then we have an independent assessment panel that ultimately makes the decision on whether we're able to do a project, and then we do that 250 hours of work. So just as a snapshot of how we've progressed over the last 14 years. So I think we're actually over 125 projects now. We did a quick analysis to try and see how much capital had been raised by some of our alumni just over the last 3 years. It's probably much more than that. It can be quite difficult because we've got quite a large breadth, and it's hard. Not everyone is, we're not that well connected to capture all of that, but at least $30 million. We've assessed more than 750 ideas. Every year we have 100 people from more than 50 organisations contribute. So it's a big operation, growing up over time, and some examples of companies across the top there. We're also partners on some MTP Connect grant programs. So MTP Connect is the National Growth Centre for MedTech and Pharmaceuticals. We have representation on the medical device streams for both BTB and TTRA. we're the sort of the medtech lead, and then for the one in the middle, CTCM, which is medtech specific, we're one of the 3 partners in that. So national. So, and I should mention that this is a national program. We have funding again through MTP Connect to run our ideas incubator nationally, but also running these national grant programs, which are sort of a follow-on from that ideas incubator stage. So it's helping companies to progress towards the clinical trial stage. So we've got good breadth in terms of the companies that we're working closely with. I just thought I'd quickly mention we also have a capability directory, so if anyone's interested, you're looking for local or national manufacturers, we set this up a few years ago, so it's really just pulling out all the information that we've gathered over the last 14 years with people separated by different tags, so you'd be able to find any manufacturers. I have a few case studies. I think I'm already probably taking up quite a lot of time, so I won't go through every case study. I'll probably just focus on some of the more important ones. So I'll skip that one. So we did some work this is a South Australian company doing so it's really a different type of pacemaker insertion procedure. Previously, you didn't really have to be too targeted because most people getting pacemakers didn't live too long, so the procedure was quite simple. More recently, there's been a move to physiological pacing, which involves targeting a very specific area of the heart. It seems crazy when people come to you with these issues, but actually they're removing alligator clips to switch between reading the signals from the heart to being able to insert or deploy the lead into the wall of the heart. So in the process of detaching the alligator clip, the clip can move, and then there's no way of double checking that. So we developed a very simple device that would address that issue, but also developed a rig that meant that they could simulate that procedure to show. So we're using conductive rubber, simulating the ECG signal with a bullseye, so they had to get right in the right area so they could practice using it. So that meant that they could go and demonstrate that to some of the large medtech companies around the world and apply for grants. So, and I'll skip over some of so just quickly, near-morph mouthguards. This was a dental hygienist who had been a bit fed up of having to pull mouthguards out of kids' mouths when they had braces. So they were playing sport, they'd have cheap mouthguards and they'd get stuck, so she was constantly pulling them out. So what she wanted to do, she was originally importing mouthguards, again, some with good qualities, some not so good qualities. And so she'd sort of developed an idea of combining a few different technologies, had no idea what to do. She was a dental hygienist just selling these mouthguards, came to us. Not only did we connect her in with the material scientist to help develop the 3-layer polymer, but also gave her advice around the commercialisation. So she manufactures these in Adelaide, and she's selling them across the country, including to some AFLW players, as you can see in the bottom left. Another one, so this was for an orthopedics company. So this is a product for helping to fix femoral nails. One of the issues that they have is that they do lots of x-rays, and the challenge is that you can't see where the distal end, so the end towards the knee, so the end where you put the nail in, very easy to spot, very easy to screw the nail into the bone. The far end, you have to use x-ray. You want to check the orientation, can be very difficult, uses lots of x-rays, takes lots of time in theatre with very expensive orthopaedic surgeons. So this device runs a current along the length of the nail and uses a couple of sensors to measure the positioning and guide the drill, so it saves lots of time. And that's for sale in 30 countries around the world. And finally, I don't think I'll get on to my final part, but another example of a company that we worked with, we did, in this case, some environmental test lab validation work for a company called Plasma Shield. They do air filtration, and one of the benefits of this, so they're using E-beam, so where most filtration systems are, you use a filter, it means that you need to have more air conditioning units to pump more air through. This is sort of a non-filter based system, so what it means is you can drop the number of units that you have running, so there's a cost saving to the company, to the ventilation company supplying the units, and they put some of these in and it provides comparable decontamination. Finally, I think this one's probably come up in previous presentations, but this was a good example. So this was a Uni-SA project developing microfluidics, so that was done at ANFF-SA in Mawson Lakes, to develop microfluidics that can measure a couple of biomarkers that are important in measuring preeclampsia. So once they'd sort of proven that the technology would work in around 4 patients compared to the current gold standard, they'd come to MDPP, and what we did was to sort of concurrently, at the same time as they were developing the sensor, we developed the benchtop reader. As Craig mentioned, I'm a mechanical engineer, so I don't really understand the electronics, but I'm assured it's very, very complicated, the sort of the design requirements, and our electronics engineer is here today, so I'm sure he'd back that up. Difficult in terms of reading out that the data. So we did a lot of work to develop the benchtop reader, which puts them in a really good position, because not only have they sort of validated the sensor, but now when they go to trials, they're able to do the testing in the hospital on real blood samples, so they're at that stage now. And this was a great collaboration between the 2 sites, both at Uni-SA and at Flinders, because, yeah, we've sort of worked concurrently on these 2 different elements to bring it together, and still do lots of ongoing work on that one. So I'm not going to talk too much about this. I'm going to flick through lots of slides before Belle kicks me off. But one of the issues that we have identified, so there's a lot of requirements in terms of medical devices. Different classifications mean that you have different levels of quality management system and compliance that you need to perform. And this is a big bottleneck for companies at the moment. I know we've seen a lot of talk recently about in the pharmaceutical industry through COVID about the requirements for trials. Medical devices are a little bit different. We don't have the 3 phases in the same way, but we do have a pre-market pilot and a pre-market pivotal, and there's a lot of requirements for companies to have set up a quality management system in order to get to that. The problem was we don't have a lot of expertise in the country to do that. We do have some companies that will take on legal responsibility for you, but then you're stuck with another company being your manufacturer. There are consultants which charge you lots of money to set it up, but they don't necessarily teach you how to run it, and it's a big undertaking to try and learn how to do one of these things. So all of this documentation is all publicly available. ISO 13485 is the quality management system, and there's a whole process behind how you set up, how you navigate. And really the idea is that, so when the regulators in different countries want to come and audit what you've done, that you have a standardized documentation system, so they can say, well, where's this document, and they should be able to see how it all fits together, so it makes it much simpler. That's standardized across the world, so everyone has to fit that, and the problem is that it can be quite difficult, especially for a startup. And if you are a startup and you want to get to clinical trials, you need to go through this process. You don't need to be accredited, but you need to go through the vast majority of this process to do your clinical trial, because you're going to use that on patients and there's a risk to the patients, so they're not letting you skip these steps. So one of our future plans, and again this is through ANFF, is to set up a facility that will help to train people in how to set up a quality management system. The aim is that we'll do sort of on-the-job training, so companies will come and be based with us for a period of around 12 months, and we'll train them in how to set up a quality management system and have access to, particularly to some of the testing and validation equipment required to meet some of the regulatory requirements. And that's it. Thank you.
Okay, I think that was a really good. I love these last 2 talks of the week, because on Tuesday, remember which day of the week it was. On Tuesday, you had Harry from NASA talk about the TRL scale, from TRL 1 right through to about 9, and what it means to go through that. And what we're seeing here is a mechanism to help support some of those inventions and ideas to actually achieve the higher TRL levels and become businesses. And so we'll hear a bit more about what it means to do that. Any questions for Stephen? Oh, yes.
Thanks, Stephen. Really interesting presentation. So actually, it's a great segue talking about TRLs. What TRL or what stage of maturity would
Yeah, it's a good question, and it does change a little bit depending on the device. So it's not an easy question to answer. So so sometimes we'll get a surgeon who comes with something scribbled on the back of a piece of paper, but it's a mechanical device, so there's not too much inherent risk, so that sort of fits quite nicely. When it comes to anything sort of along the molecular biology type lines, we need some. So the preeclampsia device, as an example, they tested it on 4 patients. Well, I can't remember if it's on 4 patients or 4 representative samples relative to a gold standard. So that works quite well. So it's early stage, kind of depends. But if in doubt, I'm more than happy if you've got a particular project, I'm more than happy to discuss. Yeah.
What's the average duration that it takes from an idea to a prototype and then from there, going through clinical trials and to a commercially available product?
Yeah, that's a great question. It's almost like I planted that question. Yeah, so just as an example, so we had one of the examples that I skipped over was an orthopaedic surgeon that had a knee rehabilitation device. He came to MDPP 10 years ago. He'd been working on that device sort of 2 or 3 years before that. He got TGA approval last year, so it's taken him more than 10 years to do that. That's a bad example, which is why we want to set up a facility that will help. It does completely depend on the project. Probably one of the biggest barriers is funding. It's similar to pharmaceuticals. It takes a lot of money to get through the trial stages, so that can often be a barrier. So there's no real set timeline. I would say that so that example which took 10 years, he could have done it in 1 year with the right processes in place. For most companies, I'd say anywhere between sort of 1 and 3 years is probably pretty normal. But then again, it also depends on the classification of the device, because a Class 1 device is very simple. A Class 3 device is implantable, much more difficult. So it's a big open-ended question, but we could be a lot quicker than we are now.
So Stephen, would that be one of the advantages of having something like MDPP there, so that people with ideas who aren't really sure about what that path to market is can come and understand it for their specific situation?
Yeah, and one of the reasons why we're talking about this bigger facility is so between the fact that we've got this ideas incubator working with very, very early stage ideas, between some of these grant programs where we're working nationally, we used to think maybe this is an Adelaide problem. It's not. It's a national problem. We see companies all over. So we're already giving a lot of advice around this, and we already see that there's gaps here. So really, we're just building on the fact that it's frustrating for us to have worked on a project 10 years ago to watch it slowly eke towards TGA approval. And that was lucky because it's an orthopaedic surgeon and he's got lots of money, so he can carry on supporting it. But in many cases, what we're doing is we're developing the technology. We're making it so difficult for companies to get that product through the regulatory barriers to get to market that most of the time either patents are lapsing, they're giving up on technology, or they're sending it offshore, and other countries are commercializing the IP that we generated. We're very good at generating the R&D and early stage ideas, but we're not very good at the next steps. And that's partly because we don't have the funding here as much as, say, the US, but we just don't have the expertise, so we need to develop all of that.
All right, well, for time, I think we'll close it there, but please chat to Stephen at lunch, and I'm not going to forget to give you your gift. Thank you very much, Stephen.
Thank you.
Do we have Leanna's talk? Belle, is it already on here?
It's on the desktop. Leanna, yeah.
Okay. Okay. Excellent. How about that for the last talk of the week, where actually I'd say that was seamless. You know, eye of the beholder and all. It's my absolute delight to introduce to you Dr. Leanna Reid. I've known Leanna for many years. We're both still young, as I like to say. She has had many roles, and there is no way that my introduction is going to do justice to all of it, but I'll just briefly read you what we've got here, which is a little bit, and then I'll say something myself. So Dr. Leanna Reid is the Chair and Managing Director. Is this still up to date? Yes. Probably not. So I'll just read this part. Leanna brings extensive experience, extensive research, executive board and investment experience, particularly in biotechnology, and she's the former Chief Scientist for South Australia. She's is chair of Carina Biotech and TechSite, and her government board memberships include, this is where I think it is out of date, is it?
I've got some up.
Okay, so, but that was the part I was just going to read because this is what we had, and it's always changing with Leanna because she's extremely busy and active. But I wanted to say this, is that as I've seen Leanna over these years, as I would say that she's really an outstanding scientist. She's a leader, she's an entrepreneur, she's a pioneer, and I'd even go as far as saying, and she'll probably blush, as a champion and a hero for science and engineering in our state and in Australia. So that's my introduction, Leanna, and it is a great privilege to have you speak to us today. I'm absolutely overwhelmingly excited to hear what you say today, so the floor is yours. Thank you.
This one. That's all right, I'll get it in a moment. So, that's it. That's right. We have to evaluate a lot more, and it is changing since I put this rather cynical slide together of digging it up or growing it and shipping it out. And the program that Stephen mentioned is the sort of thing that really is helping to transform us in some of these areas. My innovation journey, as I call it, just to give you a very brief profile of where I've come, which of what Craig was saying. I'm a scientist. That's my only formal training by background. Agricultural science, actually, to start with. But then moved towards the medical sector, PhD, postdoc, pretty traditional stuff. I had a tenured lectureship at University of Adelaide, which I actually quit the day my tenure came through. That was totally coincidental. But as you'll see from this, I started to realise that what actually I'm passionate about, and one thing, is putting science into practice. And you'll see the journey through there as it leads progressively that way. I then started up a thing called the Child Health Research Institute, which is at the Women's and Children's Hospital. I was only 34 at the time, so it was a bit of a, I often say naivety is a very good thing. You don't know quite what you're going in for. So that was a big learning curve. And we applied for, in the very first stage of the round of things you've probably heard of, cooperative research centres. It's a formal scheme that brings industry together with research organisations in Australia. A very, very successful model. Not that different really from the MDPP in a sense, but perhaps a more formal long-term situation. So we were successful in one of the first rounds of these back in 2000. From that, I then spun out a company, TGR Biosciences, a startup company, which is in the makes assay kits for biotechnology laboratories. And from there, I've gone on a number of board positions. Back running another CRC, cell therapy manufacturing, of which UniSA was the major partner. A very productive relationship, very strong area at UniSA. We spun out and still have, and I'll tell you more about, two companies there, Carina Biotech and TechSite. As Craig mentioned, I spent 4 years as a chief scientist for South Australia, which is a real privilege to be able to put back into the system what you've learnt. And now I'm on a range of boards and so forth, which I'll show you. So this is the things I currently do. Some people would say it's a bit much, but actually they don't all take the same amount of work. And they span research, industry, and government. Strong focus on biotechnology, because that's my background, but you'll see applicable to a whole range of things. Uniseed, for example, is a venture capital company which invests in all sorts of technologies across the board, or the Ag Tech Advisory Group for the state government, so back into the ag space, RSPCA and so forth. So a whole range of different things, and I think that's an important point to say. Here I am, a scientist, just a base scientist, did a PhD, but gone into all these different sectors. So how do science skills fit with business? You might think, oh, I'm a scientist, I couldn't possibly go into business. But I think if you think about what you learn in science, it's actually very, very applicable across to the business sector. So what do you do in business leadership? Well, you've got to work out the strategy for a company if you're running it. You've got to finance it. You've got to know that you're competitive with the rest of the world, because we're a global sector these days. A lot of technology, particularly in science-based companies. You've got to manage people. That's probably the biggest thing that makes companies fail, is you don't manage the people well, be they your stakeholders, customers, or your own people. You've got to oversee a whole lot of operations in all different aspects of the company. Risk, of course, is a problem, and complying with all sorts of regulatory gumph and stuff. Well, when you go across to being a scientist, well, the base thing you learn, actually, is how to solve complex problems and think outside the square. And you can use that in anything, literally. So think about that. You're not pigeonholing yourself by whatever degree you are doing. You are learning skills which are transferable. Raising funds. One of the banes of scientists' life is having to raise funds all the time. Ask Craig here about it. So same problem. Being innovative, creative, be it a business model or a scientific problem. Obviously technology comes in a lot. Culture and people, well, science these days is very much about teamwork. You don't do it on your own anymore. But logical, critical thinking, thinking outside the square. And you certainly have to have a lot of deal with uncertainty and risk. So think about that, and those skills that you're learning every day here, you can transfer them to a whole range of different future career paths. So why did I choose a career path to business? Well, I didn't think of myself that way to start with at all. Started out fairly traditionally. I didn't even think that I had any leadership capabilities. Sometimes I still wonder about that. But I knew I got a buzz from several things, and that progressively grew on me. And the first one, as I mentioned before, was putting science into practice. I left the university not because it's an unsatisfying career, but I thought, well, teaching is very, very important, but it's just not for me. I want to be out there putting that science into practice. Strategic planning. I love, planning big operations and so forth, and large collaborative ventures. So not doing something in a lab on my own, but cooperative research centres that involve lots and lots of different partners and lots of people. I didn't realise these things to think of, and you're probably sitting there today saying, I don't know quite where I want to head. So I guess what I'm saying today is if you think about the things that really you get up in the morning and think wow about, what are you passionate about? Think about how that takes you in your career direction and where you might head to make those things work, because that's what you're going to enjoy life on and do well at. So some learnings briefly for building. You know, I think I've been involved with building a number of successful innovation enterprises, be they cooperative research centres or biotechnology companies and so forth. Well, the first lesson probably goes back a bit to what Stephen was saying, is think about solving an important problem, be it in industry or public sector, rather than, gee, I've got this little widget, I wonder what it'll do. Because you're trying to put, in that, if the bottom-up approach is important in science, because discovery research is crucial, and people are understanding, you know, mechanisms of some cell pathway or whatever, and that's very important because industry builds on that wealth of science background. We couldn't do it without it. However, too much we focus on the widget I've got and what I can do with it, put the square peg in a round hole. And I'm sure Stephen's seen a lot of this, where people come along and say, oh, I've got this great concept. They haven't thought about what, does the industry or whatever is the ultimate customer really want and need that? And what stops something getting to the market is often not related to the science. The science can be fantastic, but there's all sorts of other regulatory issues or whatever else, competitors that come in and just, you know, put their foot on you, and that's the end of it. So focus on an important industry problem. And I'll give you an example of that from Corinna Biotech, and a little bit of background on this. Corinna Biotech is one of the companies that spun out of our Cooperative Research Centre. It's in immune therapies. That is where you use the immune system, modify it to attack a disease process. This is called CAR T therapy, chimeric antigen receptor T cells. Now this is the beauty, I mean, this gives you goosebumps, this stuff, because when they first introduced this, what they did was take out your immune cells called T cells, one of the immune cells, engineer them to recognise a cancer, put them back in the body, and they gobble up the cancer. And when they first introduced this, not that long ago, 2015 or so, they put it in with blood cancers. That's the low-hanging fruit, because they just circulate. Sorry, am I doing this? We're just circulating around in the... Oh, it's a pendant, sorry. I'll put it up here. Well done. They put it into some patients who had end-stage lymphoma, because you're not allowed to give these new therapies to people as a first-line therapy. They have to have tried everything, chemotherapy, radiotherapy, whatever. 3 months left to live, most of these patients. They gave one dose, took out their immune cells, engineered them to recognise the cancer, put them back in, and one treatment, these patients, 90% plus, are cured, not just controlled, cured. It really is the future of cancer therapy. Probably in 20 years' time, we'll be saying cancer, yeah, all right, go and have an immune therapy. Well, what Corinna did was identify a cancer-specific target because lymphomas were one thing, but solid tumours are much more difficult. All sorts of reasons I won't bother you with, but there's been no success so far in solid tumours for CAR T therapy. So Corinna said, well, what's the problem? And the problem was finding something that specifically targeted a solid cancer, but would not touch any normal cells, because you can't destroy your liver while you're giving yourself immune therapy, for example. Now what we did, we'd never even worked in this field, so we did a literature search and a patent search, and we said, okay, we've got this target we think looks pretty good. That's what the industry's saying we need, is a target for solid tumours. We actually put a patent application in without having done any work whatsoever, which is totally the other way around. Normally, you know, you've got a light bulb moment, you come up with something and I'm going to patent it, then I'm going to, you know, work out what to do. We did it the other way around. And then we did the work to validate it. Actually, the target we used to start with was already patented in the literature, but no one had even thought about patenting it for CAR T therapy. So we patented for that. When the company who had that patent for cancer therapies, not CAR T, found out that we had the patent, they were not amused. We ended up actually selling it to them, by the way, this particular target. Anyway, just to show you the efficacy of this approach that we found, this is a video of a tissue culture dish, and and that pale background you can see there is a nasty breast cancer cell line. And the green cells are the immune T cells. And these are normal T cells, nothing's been done to them. And you'll see they wander around, they almost like the sniff, and they go out and they suss out the cancer and say, no, that's all right, I'll leave it alone, and so forth. What we then did was to genetically modify actually the same CAR T cells from the same patient to recognise something that was on that cancer cell that it could target. And this is the effect that you get. You start to see the T cells say, hey, something good's going on here, and they all start gathering in. Then you'll see a lot of red appearing because there's a dye in there that when cells die, they'll turn red. So that cancer cell in the background is progressively being destroyed. You'll see it sort of disappearing on you and going into all these dead clumps. So within minutes, this CAR T cell was recognising and killing the cancer cells. And we've gone on since then very successfully, and this is solid tumours in mouse, now not on a tissue culture dish in mice, and they're implanted with a tumour. UT is untreated, and you'll see that's the line going up the top, so the cancer grows, it's a breast cancer, grows very rapidly, whereas the bottom line is the mice with the same tumour injected with our immune therapy CAR T cells, and you can see it just totally destroys the cancer. So we're about to get, we hope, the FDA approval to start a clinical trial on this. So it's a real buzz to sort of actually develop this technology and now be actually going into humans, and we hope being one of the pioneers of curing cancer, solid tumours with CAR T cells. But the bottom line was, the reason I said this, is that we did it the other way around. We said, that's the problem. You've got to find something specific for solid tumours. Let's develop something, patent it, because you have to have patents in this field or else you'll have no competitive position. And it's looking very promising. So a second learning is that you can't do it alone. And I think you've heard that story from Stephen very strongly already. There's a lot of expertise that's needed there. There's no way that you can do this with a little company focusing entirely internally. But it's difficult for a small company because you haven't got much money. You can't go out and appoint everybody that you need to be appointed. So what we've done, both companies, is one is to get a very strong independent board that really understands where we're headed. And has all the networks internationally that we can go with, and also advisors and partners to work with internationally, because this thing is not an Australian problem. Australia is a very small market for this sort of thing. And in both cases, we've got some industry leaders who have come on board and really been helpful. And Mike Jensen, for example, is really one of the pioneers. He actually was one of the inventors of that immune therapy for lymphoma that I mentioned to start with. And we thought, oh, well, it'd be nice to approach him. And then we thought, oh no, he'll just, we're a two-bit little company in Australia, he'll just tell us where to go. But we went along to him, and he's so generous. He's a paediatrician, they're always nice people. And he's really helped us along the journey really solidly. So don't be afraid to knock on doors, even though you think, oh, they won't listen to me. Some won't, some will be so-and-sos, but a lot of people will really help you out. The other, I guess, is that what makes a successful company might not be the first thing that you start out with. In the case of Carina, it looks like it is, but our other company, TechSite, is a bit different. What TechSite does, also from the Cooperative Research Centre, and this is very strongly UniSA originating territory, particularly from Professor Rob Short, who is no longer here, but a very leading person in this thing, is to create coatings for medical devices in this case. And that coating helps stop them from blood clots forming and so forth when you put them implant them in the body. So stents are used, for example, to open up blood vessels which have become blocked. Now this is working very nicely. Sorry for the gory photo, but here's an example in a laboratory situation where what we call bioinvisible, that metal stent is coated the one on my right, with our coating, which is just a chemical coating, it's not a biological thing, and used in a loop of blood. And you can see the one that has no coating has clotted very rapidly, whereas bioinvisible stays unclotted for hours and hours. So it's proving very effective. And we're developing this nicely in this market. However, what we recently thought was, well, where else is biofouling a problem? And one of the big areas, which may end up being the real success for the company, is in the industrial filtration area. So be it treating wastewater, food processing, and so forth. The desal plants, for example, you all use membranes which they get particles building up on and causes real problems. And we're just getting some very good early results with that. So for all we know, TechSite, which is a medical device company, could well end up being an industrial filtration company in its success. So you're just thinking outside the square, where else can we apply this? And then finally, how do you get money for all this stuff? That's a real toughie. And usually when companies first start up, there's a little bit of money there from, as it's often said, the 3 Fs, friends, family and fools, and so forth. But then you get to the point where you need a bit more, and where do you get it? And unfortunately, venture capital is not always the answer. That's the sort of big money, and you certainly need that if you're going to go. Carina, for example, it's just finishing a raising for about 8 million. Next one, it'll burn that within the year when you're going into clinical trials. Next raising is going to be 25 million, so it's not trivial money. Unfortunately, Australia is not very good at this. We don't really have that depth of funding, so we're probably going to go to the US for that. But the first one might not be the right one, and venture capital is not for companies that are not really high growth, for example. So it may be tempting to take money up from the first one that comes along. It's not always the right decision to make. So I will conclude there, and with a statement, as I said, started out with saying, you know, science training gives you all that problem solving, thinking outside the square, innovation. You can apply it to anything you choose to do so. And I wish you the very best for your careers. Thank you. Yeah, you're going back into it. Yeah.
And this might be a bit of an awkward question from the uninformed, but it's what I've sort of recently come to understand is ANFF and NDPP are effectively non-commercial. And there's always a lot of talk about lack of funding, particularly in education. Are we leaving money on the table?
And leaving money on the table for?
Well, for the research and the work that's being done. I understand that there are widespread benefits to the Australian community, but for the education community, are we being too nice?
Being too nice. So you think the funds are not being used to practical benefits sufficiently?
Could the education sector see a better return on the funds that we have?
So I think you mean sort of, so there's technology transfer offices that take a position in some of the spin-out countries, so they'll still retain our fees. The universities can still sort of make some money on research. A lot of the programs, so I mean, mostly kind of through government grants, and the government do a lot of work in early stages.
I'd put two perspectives on that. One is you don't want everything to be commercial. So you wouldn't want, if you were going into it saying, oh, we're only going to do this if we as a university or whatever get a return on it, the world would miss out on a lot of important research. As I said, everything I've talked about here builds on such an enormous amount of fundamental research. It goes back years and years. There's no way that you could return to that. So that's the role for government to fund. And private enterprises, Cancer Council, all sorts of things fund that sort of thing. So there's a very, very important place for that. And in other aspects, I mean, yes, I mean, if it's going towards the commercial sector, then university should benefit. In our case, I didn't go into the structure of the Cooperative Research Centre, but for example, UniSA is a shareholder of both TechSite and Carina, probably owns, 10% or so. Well, Carina is current valuation is 30 billion. TechSite is less than that, but it's heading towards that direction. So it's actually potentially a very important source of funding back to the university. So horses for courses, I suppose, in terms of what you're applying that to. Mm-hmm.
So the stents are good at stopping blood clots, like clotting through the blood running through the stent itself. But how effective are they in stopping the arterial tissue running through the stent and blocking it up that way?
Good question. That's restenosis. So you've got thrombosis as a problem. That's the blood clotting, and restenosis, which is the cells growing into it. I mean, mostly what happens is you don't get blood clots that badly because healthy people are okay. If you're a heavy smoker and all the rest of it, there are some blood clots. The restenosis is a problem not so much in the coronary, the heart, but in the peripheral ones where they do that. So I didn't show you the data. Sure, it's a very nice. We're just doing a study at the moment with scientists from SAMRI. She implants stents into the coronary artery of mice. Now, I think if you can imagine doing surgery on the coronary artery of a mouse, it's bloody impressive stuff. These are things about 1 millimetre across, so she's a very good surgeon, clearly. And we have done some studies with that, and the coating actually totally stops the restenosis. So, yes, these things are problems. Not in the majority of patients, but they are problems with that kind of thing. Mind you, not having a stent's a problem because you've got to...
So you've seen everything from being from a university perspective all the way through to chief scientist and now moving into industry. So from your perspective, your last learning number 4 was to basically say that you've got to plug my straight for investment. And well, what do you see as I guess what needs to change in Australia to enable that?
To enable that to happen. Yeah, we've got such a shallow investment amount. Like, I mean, the same company, Carina, which has raised 8 million, which is pretty good, in the US would have probably raised 50 million at the same stage. It's that sort of depth of market. So I guess it's getting a bigger investment pool and the quality of people to manage that and make those decisions. And that's changing. We're learning that sort of thing versus 10 years ago to do that. And there's a range of different means. I mean, the angel investment area is pretty important. That's for small-scale funding. I'm a member of Southern Angels here, which puts your own money, money and mentoring into small companies. So I hope it changes because the problem is that when you need big money, the tendency now is to say, we'll move the whole company to the US. And then, then we're back starting again. So I'm determined we can try and stay here. We will have to get US money, but, hopefully we can still stay an Australian company. So a very good question, big challenge. Progressively changing won't happen that quickly. Yeah, absolutely, yeah. One other approach to that too, if I may just add, is that think about a business model that has some cash flow instead of just big burn, which it tends to be in the pharmaceutical sector. TechSite, for example, makes about $1 million a year in research contracts, which it does for pharmaceutical companies, where it says, we've got expertise in coating implantable devices, I can solve your problem. And so it buffers the need for investment money with cash flow, and I think that's a pretty important, in our environment, that's a pretty important approach.
I'll ask one final question. Over the years, there seems to be a bit of a shift that students who do PhDs are not always going for professor roles, but the new tenure track.
There aren't many on offer, are there?
There aren't many on offer, and but we're seeing, I think, a changing landscape where industry is recognising that. Is that the case? And what would you say as to undergraduate students, PhD students about career, what would your career advice be to them?
Well, first of all, as I said before, think about what you get a buzz out of. Because if you get a buzz out of doing fundamental research and just doing that work, then maybe industry is not the path for you. It's still, we do, as you can see, the company like Karina does some pretty impressive basic science. So it's not that you don't do it, but think about that to start with. But then if it is towards industry, again, that's probably improving, but we're nothing like Germany where, you get a PhD and of course you're going to go into industry. We don't have yet, it goes back to that slide I showed about digging it up and shipping it out, we don't yet have the range of innovative companies that would... But, having said that, the company CSL, everybody knows CSL, wouldn't you? Do you realise how big a company that is? It's about the second biggest market cap company in Australia. So most people don't realise that, a number of these companies are actually doing, it's not just banks that make money these days. How do you do that? I think the Cooperative Research Centre program is a very powerful one because as a postdoc, for example, you could be involved in a research program that links the researchers together with industry. You learn those skills on the job and so forth, and it puts you in a skill base that perhaps is more attractive to industry and so forth. Thank you. Thank you very much.